we'll get into the floating offshore wind deep dive, innovative design solutions. I'm Monica Kumar, and I'll give a brief presentation from DOE, and then we'll have our 3 NOWRDC project presenters. So I'm Monica Kumar with GDIT in support of U.S. Department of Energy's Wind Energy Technologies Office. And just to get into a little bit about DOE's floating offshore wind portfolio. So as we've all heard, about 2/3 of the U.S. offshore wind energy potential is over water that's too deep for today's fixed foundation designs. So that means floating offshore wind energy is going to be key to transitioning coastal cities to clean energy. And it'll be a big industry, so floating offshore wind will mean thousands of high-quality jobs in manufacturing, installation, and operations. So by ramping up R&D efforts now, the United States has an opportunity to become a world leader in floating offshore wind energy system, both design, development, and manufacturing. So the floating offshore wind shot was announced in September. So it sets an ambitious goal to reduce the cost of floating offshore wind energy by 70%, so down to $45 a megawatt hour by 2035. And at the same time, BOEM announced an associated goal of deploying 15 gigawatts of floating offshore wind by 2035. So the floating offshore wind shot is a very ambitious goal, and R&D contributions towards the cost reduction could be made across several areas, so upsizing turbines with higher generating capacity, serial manufacturing and design for fabrication, systems engineering and optimization, increasing operational reliability through both improved operation and maintenance, as well as lifetime extension practices. And to recap, there were several co-announcements that were made on DOE's floating offshore wind efforts along with the shot. So that included ARPA-E's Atlantis 2, which will focus on experimental testing in ocean, lake, and tank and tunnel environments to further develop new technology. NREL is leading a West Coast port strategy study to develop a ports network and identify upgrades needed to deploy floating offshore wind. NOWRDC also announced 5 new awardees. And WEDO announced it's funding its first ever prize, so the Floating Offshore Wind Readiness Flow-In Prize. In that, competitors will help develop a domestic supply chain and accelerate market readiness of U.S. floating offshore wind energy designs. And WEDO and BOEM announced that EPRI will conduct bat acoustic monitoring along the West Coast. NREL is developing a set of modeling tools to help industry and researchers design commercial scale floating offshore wind in the array scale. And PNNL is conducting a literature review of West Coast wind transmission related studies along California, Oregon, and Washington coastlines. So to elaborate a bit on that Flow-In Prize, which might be of interest to those who are here. So it's currently open. It's a 3-phase prize. It's a $6.9 million competition designed to pave the way for cost-effective domestic manufacturing and deployment of commercial-scale floating offshore wind technology in U.S. waters. So the goals are to advance designs of turbine platforms for manufacturing, improve the supply chain readiness, to enable mass production and assembly, to lower associated costs, and as well as further the principles of inclusion and environmental justice that are embodied in the administration's Justice 40 initiative. So some of the efforts might include design and assembly changes to floating offshore wind platforms, innovations and adaptations to facilities, tools, ports, vessels, and processes, integration of full-scale system to design, build, and installation. And another effort coming up, so for those who are part of a small business, There's an upcoming small business innovation research and small business technology transfer funding opportunity. So it's planned to be released on this coming Monday, December 12th. So the Wind Office, WIDO, is supporting an open call. So that includes, but not limited to, floating offshore wind. And in the past, floating offshore wind anchoring technology SBIR projects have been awarded and advanced to phase 2. So this year invites applications for technology innovations from distributed, land-based, and offshore wind. And there's also other offices within the Office of Energy Efficiency and Renewable Energy that also have SBIR topics open. And one more announcement. So DOE currently has an RFI open seeking information on mooring and anchoring systems for floating offshore wind. So it would be great to get input from anyone who has mooring system expertise or ideas. Responding to the RFI does not limit your ability to apply for future funding, and it's a great opportunity to give your input to help shape the future R&D directions. Encourage everybody to check that out. So with that, I'm excited to start the NOWRDC Floating Offshore Wind Deep Dive. So in this session, we'll hear from Zach Miller from Triton Systems, John Halkyard from Deep Reach Technology, and Jose Serna from Esteco. And so there'll be a Q&A portion at the end of the session. So questions can be submitted through the Slido app, both in person and virtual attendees. Great. So welcome, Zach.
All right, great. Thank you, everybody, for being here. My name is Zach Miller. I am the Chief Technology Officer at Triton Anchor. We are a developer of a new anchoring system. This project was funded by the NOWRDC. Previous funding has been given in a total of about $5 million from NOWRDC, US DOE, Massachusetts Clean Energy Center, and then US Navy prior to that. We are located right outside of Boston, about 20 minutes in Chelmsford, where our facility is. We have a small fabrication area, high bay facility, testing area, and engineering set up there. Our mission here is to provide a cost-effective anchoring system for the offshore renewable energy market, ultimately solving a lot of the issues that other anchoring systems and problems they have. As Monica mentioned, so Triton Systems is the company that has the NOWRDC contract. Triton Systems is a technology developer. We develop technologies across a variety of industries. Because of the success of this program and this project, ultimately trying to commercialize technology, we have spun off the company Triton Anchor. So Triton Anchor will have its own mission and business model going forward, and will support the product. We have taken outside investment as of October. We're very excited about our future, backed by OS Impact Investments and then Massachusetts Clean Energy Center, also from their investment side. So ultimately here throughout this program, we've been focusing on these 6 main items that we see as the industry needs or the problems that we're trying to solve with our anchoring system. The current solutions are very expensive, and they're only manufactured in low volume. So as the high volume increases, the costs don't go down significantly with the current solutions. The existing local infrastructure is not suitable for the manufacturing, transporting, and marshaling of these huge anchoring systems. So we're looking at being able to develop a system that can be produced locally to the ports of interest in the states and creating that local content. Floating winds needs anchors that allow for different loading conditions than offshore oil and gas. So either high vertical load conditions, shared anchors, shared moorings, multi-directional. There's a lot of different combinations that this new anchor needs to be adaptable to. Environmental impacts. A lot of the old solutions, as in driven piles, they emit noise during installation, or drag anchors require a significant amount of chain on the seafloor. That's not going to be acceptable going forward with these environmental impacts. We want to make sure we create a solution that reduces these objections by stakeholders. We don't want anchors to be the limiting technology. We want anchors to be the enabling technology of better floaters, better mooring solutions. Right now, anchors, specifically maybe for TLP, are a limiting solution where they cost so much. So we want to enable other technologies, not take back from that. Then ultimately, removable solution that helps facilitate decommissioning. So what is our technology? Our technology is based around helical piles. We are using helical piles in quantities rather than sizing up the helical pile. We're using commercially off-the-shelf sizes that they use in land-based operations. We're using that in high quantities combined with an exterior caisson to provide a systems level approach to hold the required vertical and horizontal capacities. Our system is platform and mooring style agnostic, so we can use a variety of different technologies with ours. Ultimately, throughout the program, we've evaluated several different advantages, but here are mainly 5 advantages that we've seen from our technology related to others. It's lightweight and efficient, so helical piles have a better capacity solution than friction. So helical piles get their capacity in bearing, which that make them more efficient than friction-based solutions and uplift capacity or uplift scenarios. So they have lower weight to capacity ratios to save weight. By separating out the helical piles, get the vertical capacity, and the caisson gets its horizontal capacity, we're able to be very efficient in the way that we size our anchor for bigger turbines. All of our components of our technology are easily manufactured locally. We've been working with manufacturers both on the East Coast and the West Coast to make sure that we're not requiring specialized equipment that only is in high built-up areas, as in the Gulf of Mexico. Our solution is silently installed, so there's no extra bubble curtains or acoustic emission requirements necessary. And it's versatile, as I mentioned. It can handle a variety of different soil conditions, sands, clays, layers, things like that, and any type of mooring. And it's also low cost. So one of the main activities of this program was going through the American Bureau of Shipping qualification process, their new technology process. It's a 5-stage process. This program was to go through 4 of the stages. We have completed 3 of the stages to date, and we are currently executing the 4th stage, the systems integration stage. They've reviewed engineering calculations, installation assessments, assumptions, equations, analysis, testing, and so it's been a pretty risk assessment. It's been a pretty in-depth review by third party. So we're pretty happy to receive the 3rd stage completion back at the end of September, and we're looking at completing the 4th and final stage of this program by Q1 of 2023. Ultimately, this 4th stage is accumulating in a demonstration at the University of Rhode Island Peckham Farm site. So what we have done is we have done a cone penetration test to classify the soil at that site. We have designed and built 2 anchors of different sizes and done modeling of the anchors, installed the anchors, and we will be pulling out the anchors later this year. These are the size of the anchors. What we did is we tried to make the biggest anchors that we could given road limits. So we went with 8.5 feet up in the Northeast. 8.5 feet is the limit that you can truck without extra permitting. So we went with 8.5 feet as our diameter. And then we did 2 different lengths of caisson, 5 feet and 3 feet. And then ultimately we decided to do 9 piles. This provided us some interesting non-symmetrical anchors, which helped in some finite element modeling. So to date, we have been to the test site. We have offloaded our installation tool, and we have offloaded our anchors at the site. So these are a couple of pictures of us offloading the anchors and putting our installation tool on top of the anchors. Ultimately, offshore, this would be done together, but we're doing this as a first demonstration. So this is an anchor installation sequence. So from your far left, you'll see the first photo is our tool is on top of the anchor. And then as you move to the right, you can see that we have fully installed our anchor into the ground, helical piles and caisson as we went. So ultimately, as I mentioned, we are ending here in a demonstration. So actually, I will go back here to this slide. So what we're going to be doing is this is the bigger anchor. We will be pulling out this anchor vertically. So we have hired a contractor to pull out the anchor up to the 300,000, about 150 tons of capacity. We will be using the data to calibrate our equations and our finite element modeling by displacement and force. So what we're doing is the testing is scheduled for December 20th to the 22nd. We are inviting the industry partners, funding agencies, state and university representatives to attend this test on December 20th. So December 20th will be the setup day. This will allow industry to attend, walk around the anchors, ask questions. We'll have a little Q&A session. And then the testing will occur on the 21st and the 22nd. But because of safety reasons, we're not going to have a bunch of extra people there under the high loading conditions that we'll have. So please reach out to me. My email is on the screen. If you would like to attend and receive more information, we'll have a formal invite soon. So where we are with this program and then kind of going forward. So, we've performed we're performing that field testing this month to calibrate our models. Q1 of 2023, we're planning to finish that systems integration stage and then close on the next investment round. At that point, we will be completed with the NOWRDC program. At that point, we're going to move on to completing the ABS full process, which would be stage 5. We are still waiting on the funding for that to come through but we're planning to start that in the Q2 or Q3 of 2023. At that point, we plan on getting through that certification and then scaling up for commercial contracts at the end of 2023, and then ultimately supporting more commercial bid operations and installations, smaller demonstration projects in 2024. Yeah, so if anybody has any questions, please put them on the Slido. Thank you.
Okay, hi everybody, and I want to say my appreciation to NOWRDC and giving us this opportunity. It's been a great experience working with Corey and the team here. So what we're talking about is the application of some of the novel offshore oil and gas platforms that have been used successfully in the support of turbines, wind turbines, large wind turbines. And, it's really been a co-effort between my company, Deep Reach Technology, and Trendsetter Vulcan Offshore. I'm the PI, but Jim Marr, from no relation, I guess, Monica, is also the co-PI with me. And Jim and I go back many years as part of it. So these are the topics we'll cover. On team members, as I said, Deep Reach Technology is mainly an R&D organization. My background's in hydrodynamics and analysis, and people at Trendsetter have deep experience in actually executing projects, primarily in the spars. So before we started this, we had an MOU that we would do this development together. Trendsetter, as I said, I'm in the R&D sector. I was a part of the original spar teams that started the evolution of the spars for deep water oil and gas back in the 1980s with Ed Horton, who was the inventor, and I went on to be the vice president of research at Aker Maritime and developed some of the second, third generation spars. Jim Marr at Trendsetter was the project engineering manager on some spar projects at Technip and additional projects beyond then. We brought in Gloston Associates to represent another kind of concept, the tension leg platform, which is another one of these novel platforms. They've been working on their Pellistar TLP for many years. It's kind of a spin-off from the successful Seastar mini TLP. NREL is an advisor to us, and they've helped primarily in reviewing our cost estimates. GE Global Research was part of the team. Their main effort is commenting on our installation plans, how we plan to install the cells and the turbines. And Equinor is, as everyone knows, a major offshore developer. We know them very well because many of the Equinor people worked for us on the spar platforms back 20 years ago. So So that's basically the team. The project started in September of 2021 and ended about 2 months ago. So I think we were within a month or two of schedule. You can see the different tasks we carried out there. Basically concept design, systems analysis, cost estimating, and cost roll-up and LCOE calculations. So what's the scope of the project? Well, the main, as stated, is to evaluate novel concepts that were successfully used offshore. And this examples, I think the prime examples here are the Red Hawk cell spar, which was installed for Kerr-McGee in 2004. It's a third generation spar platform. A variation of the cell spar is the buoyant tower shown here, and that was installed in Peru for the BPC field in BPC company in 2012 in about 140 meters of water. And the Pellistar represents something that's been used similar to something that's been used in the offshore industry for many years. The focus of this, what we've ended up focusing on is how to manufacture these platforms in an inexpensive way that will allow us to manufacture hundreds of them in a short period of time, as opposed to the usual fabrication methods, which take months and months to build one platform. If the BOEM example that Monica gave us at 15 gigawatts by 2035 is to be achieved, we need about 1,000 floating platforms. There's only been about 80 built in the last 40 years. So this is obviously needs a step change in the way things are done. So that's been one of our primary focuses. And I want to bring Ed Horton into this picture because he's the inventor of the spars. He passed away about 7 years ago, but about 12 years ago, he had this bright idea about mass producing of spars. And we're actually resurrecting that idea. He was in some ways before his time, but we are essentially evolving and developing some ideas Ed had back about 20 years ago, or 12 years ago. So what's the big idea? The big idea is that you want to reduce the cost of construction. Starting out with the original spar designs shown here, it typically took about 24 months to produce one using standard shipbuilding methodologies where you would fabricate a subassembly, assemble those, put those subassemblies together on a launch rail, and then you'd launch it, tow it, and upend it. That took about 24 months and 10,000 tons, $10,000 a ton. The cell spar was an innovation that we came up with in the early 2000s, where instead of using shipyard construction, you use fabrication yard construction. You roll a steel plate and you put ring stiffeners in it, no longitudinal stiffeners, minimizes the amount of welding and intersections of plates. And the Red Hawk cell spar was built in about 12 months for $5,000 a ton. Now, what we're proposing here is an automated manufacturing method where we can build one spar a week for $2,000 a ton. The material costs are $1,500, so basically it's a fully automated production line. This has already been proven in the arena of building monopiles. EEW is using this kind of techniques every day to build monopiles. And the main difference here is that you have to install bulkheads to compartmentalize the platform, and you have to install methods of ballasting. But essentially, it's a monopile that floats in a way. For this, to do the evaluations, we had to pick a basis of design. So we're using the 15 megawatt NREL IEA wind turbine with the tower upgraded to handle the dynamic loads of being on a floater. Meadows, we looked at two sites as kind of reference sites, the Gulf of Maine in 150 meters of water being one of them. The other one is the West Coast, the Humboldt Bay lease area, which is from 500 to 1,000 meters water depth. So we looked at both areas for these platforms. I mentioned the buoyant tower as one of the solutions. The buoyant tower sits on the bottom, and that would be a main solution. It sits on the seabed, and it's stabilized by buoyancy, ballast and buoyancy. For this application, because of the high thrust, we had to add lateral mooring lines to it. But basically, the buoyant tower that's in Brazil, or in Peru, is what we're proposing for this. So there's nothing, in essence, new about what we're proposing, except for the way it's manufactured. We perform sizing. Cell spars can come in any number of configurations. Basically, it's like building a stick build using like a log cabin. We found for these design criteria, we get by with one single cell. So it's a single cell spar. Now, there could be, as we go forward, there could be some value engineering that would make it more attractive to have, say, 3 smaller cells. That's part of the engineering work to go forward. The Pellistar TLP was sized by Gloston using their tools. I'm not going to go into the details of their design here. One of the things to distinguish TLP solution versus a spar or a semi-solution, I think you all know that the mooring lines of spars and semis take up a lot of real estate. So the advantage of a TLP is that it's held in place by vertical tendons, so the space between the platforms is completely free for navigation or fishing or things like that. So that's one of the big advantages of a TLP. Comparing the weights and displacements of these platforms, the spar is stabilized by fixed ballast. So every spar out there, there's 17 spars, about 60% of all the floating platforms in the Gulf are spars. They all have magnetite in their lower tanks to stabilize it. And magnetite's a very cheap form of ballast, about $200 a ton. So all these spar platforms are held upright by having fixed ballast and the center of gravity below the center of buoyancy, so it's unconditionally stable. Whereas tension-like platforms use tension in the tendons to stabilize them. So you can see here the relative percentages of steel weight versus fixed ballast versus water ballast and the vertical mooring loads. For our cost analysis, we assumed a 66 platform wind farm, which would produce 966, I think, if I do the math right, about almost a gigawatt of power. Each platform has 4 mooring lines, and each anchor has 2 mooring lines on it. Different configurations of shared anchors can be considered. You could have three mooring lines, 3 lines per anchor, and there's other permutations you can think of. But this is our basis for doing the cost estimates. The anchors we chose are the subsea micropile anchors. This is a template on the seafloor where holes are drilled and grouted to install micropiles to hold the anchor in place. The Triton anchors would work perfectly fine. I think in fact, Triton is probably better in sand and clay, and this is probably better if you have a rock bottom. So the choice of anchor depends on really what the bottom conditions are. Out in Humboldt Bay, as far as we know, there's a mix. You have some areas, there's rock outcrops, and that has to be studied. We're using a taut polyester mooring line for the spars. And the tension-like platform has a synthetic line, vertical synthetic tendons. But in each case, we're using this anchor. So the construction method is essentially similar to that used for the BPZ buoyant tower that I spoke of. It's a rolled steel plate with ring stiffeners, and in this case, we have to insert horizontal bulkheads to separate tanks for ballasting purposes. The manufacturing could be done on land, but we chose to do all the manufacturing on a barge. So all this equipment is on a barge, and it can be therefore transported from one project to another and situated locally, as long as you have a suitable area of protected harbor to put the barge in. For the case of Humboldt Bay, for example, you have an area designated for fabrication of Fields Landing to the south of the bay. There's an area for the barge just off of the ship channel inside the harbor there. So the idea would be you would manufacture the spar on this barge, special purpose manufacturing barge, which would not have to be Jones Act. Then it would be offloaded to a submersible barge, which would be a Jones Act barge. And that barge would convey the spar down to Fields Landing where the tower would be installed. So and the details of how this tower is assembled and installed have not been worked out. But in principle, we're assuming we can put the tower on at Fields Landing and take the tower and the transition piece and this bar offshore with this submersible barge. And towing these spars offshore is done all the time. It's quite a common operation. So once the spar is offshore, it's ballasted, flooded so that it tips up, upright. And there would be a fixed tower offshore to do the turbine mating. And we originally conceived this tower as being the substation. We could make use of the same tower that would be used for the substation for this operation. Although our current thinking is maybe this is a special bespoke tower that would be placed there for this purpose. The operation is to bring the spar into the tower and secure it rigidly to the tower. You have a crane, a leased crane that is set on the tower. This is a mammoth crane to set the nacelles and the blades on the tower. So it's a fixed-to-fixed lift. There's no floating to floating. The bringing the spar in and mating it is very similar. It was done on the PPZ project here. This is showing a barge with a deck on it. The buoyant tower is brought into this cow catcher, which has fendering to protect it, and is brought in and secured, and then it's deballasted and picks up the deck, and then is drawn away. So this is exactly the same operation, very similar operation what we have. This was designed for 2 meters swell. In California, we probably, to meet our economic goals, want to go for 3 to 4 meters swell, and we're currently looking at how that can be done in those kind of swell conditions. So this is the cost roll-up of all the cases. Now, the first 5 cases there are in California, and the last 3 cases are in Maine, so it should have been labeled that way. So the cost per kilowatt for this is the platform installed with the tower and turbine on top. It doesn't include the tower or turbine cost, but it includes those being installed. It runs from about $2,000 a kilowatt to $3,500. And you'll notice that the TLP costs are highly dependent upon where you fabricate the components of the TLP. The manufacturing process for the TLP is to fabricate pieces and assemble them at the site. So if you fabricate them in the U.S., you get about $3,500 a ton, versus if you fabricate them in Asia, say for California, you get $2,500 a ton. Converting all this to LCOE, we have to come up with some balance of system costs, and we used costs that NREL published for that purpose. And we took advantage of the NREL's analysis, considered I think 8 megawatt turbines up to 15 megawatt turbines. We took advantage of the lower balance of system costs for the 15 megawatt turbine case for 2030. So this is already taking into account future savings that will be in the balance of system for the bigger turbines. So you see we run from about 85 to 90 dollars per megawatt hour to up to 120. And we're using a very simple LCOE method here. And the NCFs, FCRs, those are in published reports. Okay, so that's basically the results of the study, so that we were asked to talk about commercialization plans. So right now, we're in the process of forming a new joint venture company with Trendsetter Vulcan Offshore, and that's in works right now. DRT will be a minority shareholder in that. Trendsetter and Jim Marr will be the leads for the commercialization effort. DRT's role will basically remain in the research and development kind of arena, which is really the way I functioned on all the SPAR projects that we did going forward. I was always the R&D lead. We're currently using internal funds to do a feed for the manufacturing effort. We're working with an automation company developing the feed for that manufacturing to verify that we can do this, what some people call a sausage factory, and we can meet this 1 week goal at $2,000 a ton. We want to demonstrate that before we go much further. We're also in parallel with that, we're doing pre-feed work on the rest of the processes I described, particularly the mating of the spar with the tower, the cost of a fixed tower, the sea states for mating the tower and the spar. And also, we heard a lot of talk yesterday about feeder barges. There's going to have to be a feeder barge is going to have to be carrying the cells and the blades, not the towers, but the cells and blades will be going out to the fixed tower for the mating. So we want to look at the sea states for that. So all that work will be going on in the next 6 months or so. Once we have a good handle and we feel confident in the cost, then we will go out, start talking to developers and establish a business model. At the moment, our business model is sort of in a state of flux. We have Trendsetter is one of the bigger engineering and equipment suppliers in the oil patch. They provide a lot of the subsea equipment used for production. The people in Trendsetter Vulcan, which is a subsidiary of the main Trendsetter company, they're all experienced project developers for floating spars and other floating platforms. So we think we have the capability in-house to execute this entire project. But how that building teams and subcontractor relationships and so forth is something we'll have to do over the next 6 months. It says here, build a facility. We don't think we need to build a pilot facility for this, but we do have to show through the design that we can meet our goals, and it'll have to be a cost estimate that we'll be able to stand behind. So the idea is to be able to roll this out commercially next quarter 1 of 2023. The internal feed work we're doing right now is developing these drawings and processes and plans for the manufacturing. We're about halfway through that, and the company's in the Netherlands that's doing this work, and it's looking very promising. We still think we're on target. The other thing I should mention is this sausage factory is not necessarily designed for spars. That's the pieces we develop could be configured into a semi-submersible shape or even a tension leg platform shape. So part of the work we're going to be doing over the next 3 to 6 months is evolving concepts for different types of floating platforms that could be used. There are obvious advantages to semis in some certain situations, advantages to spars in certain situations. Okay, that's all I have. Time.
Thanks, Monica. So good afternoon, everyone. I'm Jose Serna from Stakeco. I will be speaking to you about the novel concept for a floating wind solution, which we call the wheel, and how we are studying in a project supported by NOWRDC, for which of course we are thankful and partnering with NREL. It's design and applicability for the US. So thanks a lot for NOWRDC for supporting us in this and inviting us to let you know about the result of the project, and especially Corey. I don't know if she's around, but she's been managing the project and been very helpful to us. So thanks for that. Okay, so I will organize the presentation in four packages. First, I'll let you know briefly about the technology itself, and then I'll give you insight into the project, how we organize it, which are the main results. The project is a small, a 1-year project, and it's about to be completed in less than one month approximately. And I will also let you know about what are our next planned steps and prospects. Okay, so starting with the wheel technology, and yeah, here we're it's animated, but I wanted to show you, talking about the challenges and the pros and cons that different solutions have. There are, as you probably know, quite a few solutions and concepts being developed. It's a very active area, but we are focusing, let's say, on the main solutions that right now are operating on the water, be it with pilots or pre-commercial solutions for wind. This one shows are concrete. They all have their, let's say, their equivalent steel solution. And we are showing here what we see the main advantages or disadvantages. If we start with spars, I'm sure John knows very well. The spars have very good advantages in terms of sea keeping performance. They have a very natural stability concept, just keeping the center of gravity below the center of buoyancy. They are very transparent, and they have shown excellent performance. But they have a big challenge that, he showed some ideas to try to overcome, but indeed it is a problem. The mating of the offshore wind turbine on a spar, which is built horizontally, then needs to be appended. So you need to do this mating in deep waters. And up to now, they have always been happening in the Norwegian fjords, where you have very deep sheltered waters. But doing that in offshore open waters, it's there may be some innovative solutions like he mentioned, but it is challenging. And as a matter of fact, Equinor, who is the main, let's say, pusher of this technology, is now also developing semi-sub solutions. And semi-subs, similar to barges, the stability concept is based on having a large enough floating plane, water plane area, which provides inertia, just like a ship. And they bring what we see as a critical advantage, is to be able to, to have an in-harbor installation process for the turbine to make it industrializable. But then they face some challenges which are indeed solvable. But yes, they have stability with a large plane area, meaning that they are more, let's say, sensitive to the action of the sea. They are more exposed, both from sea keeping performance and the design of the mooring. And they face what we see a major constraint is the fact that with the next generation of offshore wind turbines, these floaters are becoming really, really large. We're talking close to the 50-meter radius, meaning nearly to 100-meter diameter, and that, as we will see, it's a big challenge for the deployment. What we're trying to do with the wheel technology, as I will explain, is trying to aim for the advantages and trying to overcome the disadvantages. Okay, so we're trying to maintain the very good and transparent performance of a spar system, also with a reduced material usage that this allows for, but still allow for the onshore full installation of the wind turbine with a solution that is simple to build. And what we see as something that, in our view, all the solutions have not managed to do is keeping this compact and low draft, which we see as a key aspect for the industrialization and what Monica mentioned, the need to build many of the large quantity of these floaters in an industrialized and mass production way. Okay. And how do we propose to do this? Well, we are proposing a spar system. Like John explained, this is known from oil and gas and also for some wind solutions. And this basically, in concept, is quite simple. We need a big mass on the bottom and the buoyancy provided on the top, and this is what's providing stability. But of course, you need to bring this mass down, and this has up to now always been done with a rigid structure, meaning that this has to be built horizontally, and then we have the problems that we discussed about how then to install the turbine and so on. Okay. The idea we thought is, what if this weight, instead of having it with a rigid structure, we just suspend it? This in general will not work because both bodies will not move along, which is of course needed for stability. But if we use a triangularized tendon configuration, yes, then this will just behave like a stiff structure once these tensions are pre-stressed by the weight of the lower ballast tank, and as long as we remain within certain tilts, which we comfortably do, this will just behave like rigid bars, and this brings some quite breakthrough possibilities in terms of the strategy for how to build and how to install these elements. And so as such, we call WIL, let's say, a hybrid technology, not only because we use concrete steel and steel where we think each material can be more beneficial and more cost efficient, but mostly because we have two different configurations. Temporarily, while we are building the system, we have a barge type solution, just like barges, but much more compact and much more low draft than a semi-sub or a barge system. We're talking nearly half the diameter and nearly half the draft. So for a 50 megawatt unit, our diameter is around 50 meters, which is nearly half of a semi-sub. And then for operation, we will deploy the lower tank in a system that we have analyzed, of course, a lot. And we will submerge the complete hull, going for a very transparent system, which will be effective in allowing reducing the loads from the sea, just like a conventional spar, and provide very good seakeeping performance with a big mass on the top, big mass on the bottom. This will generate very large inertias, which in turn generates very high natural periods, which means slow motions and low amplifications. It's at the end of the day a spar system, but configured in a way that it can be efficiently manufactured, as I will try to describe next. To let you know about the process we have followed in the last years to make this technology ready, it's quite a few R&D projects, counting this one, which more than €4 million investment dedicated, with quite a four tank testing campaigns, and we are also building on some experience from our bottom fixed solutions, which I had a chance also to present earlier today. It's different, but it has a lot of analogies in terms of how we build the elements and how we install the turbines on shore. And we are also building on a successful pilot unit installed in Norway. You may have heard of it. It's Tetraspar. It's a different concept in terms of configuration. It's based on steel by Stiesel. He's a pioneer of wind. And we have a good relation. We had our patent in this regard was previous, but we provided him with a license. And we are actually collaborating. And it's operating and performing quite well, although the process, it's true, the configuration, the process for installation is quite similar. And finally, I will let you know later, we are aiming for a built pilot unit of the WIL technology in 2025. Okay, with that description of the technology, I'll let you know more about the specifics of this NOWRDC project, in which again we feel really privileged to have this partner with NREL, which of course have a very deep knowledge about the wind turbine itself. We are also normally collaborating with turbine manufacturers, but of course, as you can imagine, the level of openness and interrelation and collaboration cannot be the same. And I think this has working with NREL has been great and very fruitful through all the coupled modelings, how substructure and turbine will work together, not only in operation, but also through the installation stages. And this has been great for us. We bring the expertise from civil engineering and a lot of more than 25 years working on substructure, especially for wind, both onshore and offshore. And well, I think the team really worked very well, and we do hope to keep working with NREL in other initiatives that, so we'll let you know later. We're pushing to make this technology commercial. So there are a number of challenges, but to summarize, I would say that the bigger challenge that the commercial deployment of large-scale floating wind has maybe to do with the size of the floaters we're seeing. This is maybe a semi-sub in Japan. This was for 7 megawatt. The 50 megawatt units are generating 3 times as big as a bending moment, and this was already quite large. So this is what I say. It's a big challenge to build these big structures on the sea. As a matter of fact, and it's no secret, many of the developers that are now studying the West Coast, and actually an action, the California action happening today, as you probably know, are considering bringing this from Asia, because there's really no place to build this in the West Coast U.S., which well, we're trying to see if there's a solution so that this can be done domestically. And not only with new harbor infrastructure, but even with the existing harbor infrastructure, as we'll let you know. So for that, the objectives we are going is first analyzing how our system can scale for the larger turbines, and if indeed we can do that, maintaining a compact dimension for our construction in harbor, how it could be implemented in the U.S., and how it can be based on local supply chain. So for this project, like I said, it's about to be completed. It will be completed probably early next year. The final draft is already, the draft of the final report is already in place, but it's going through revisions and so on. We did go through a go-no-go decision last May, which we surpassed successfully. And we're having several advisory board meetings with major developers who are following the project, and they have been very helpful. So the project is divided in 4 tasks, all right? First, in all of them we have collaborated, except for the 4th, in all of them we have collaborated actively with NREL about how to design this for a 50 megawatt unit, how this will behave in a coupled manner with a wind turbine, and how we can propose a strategy for industrial manufacturing these elements in the West Coast. And I will now try to give you a summary of the main results. There's quite a lot of information, so some of the slides I will rush through it. I guess this will be made available for you at the end of the session. So sorry if I cannot touch on all the information, but but it is there. And also, by the way, all the reports we have generated on the process will also eventually be made available to everyone. So the first thing we did is generate the design basis and select together with NREL and NOWRDC a reference location. We selected the Morro Bay area. Actually, initially the project aimed for the East Coast, but indeed for floating West Coast is what makes sense. And that's we generate metocean design basis and so on, which the details are not here. But with that and with the turbine, which is public, again, available, the 15 megawatt IE8 turbine, which is often used in this type of developments, we generated specific design, okay, which you have some details there. And indeed, these are large turbines and large weights, but we're managing to keep actually the diameter we're using is 52 meters, which is indeed a large structure, but as I said, much more compact than other alternatives. And like I said before, we have a tripod position piece. I don't know if I have the time of how we conceive this to make it modular and use the supply chain from onshore wind towers. And yeah, maybe worth mentioning, the total weight of concrete we're using in both tanks is around 300 tons of lightweight concrete. This is less than half than a semi-sub in terms of material usage, which of course brings economy, but also brings quite a large reduction in terms of carbon footprint, which using concrete is still already lower than steel equivalent solutions. If you then use half the concrete, then as you can imagine, you bring a big reduction in carbon. And this graph shown here is showing, yeah, what I mentioned before, because we have a large inertia, we have a high natural period far away from the waves, and therefore very good seakeeping performance, as I will let you know. We're talking periods from pitch and roll in the range of 35 seconds, and for heave even more than 50 seconds. Also, natural frequencies of the tower and the lower, the lower tank, of course, need to be controlled to make sure they are okay with the 1P and 3P frequencies. Here you have an overview of the configuration with the two different arrangements. In harbor, we have a compact low draft element. For the float off, as I will explain, we will plan to build this on barges. We have around 4 meter draft only. Once we put the turbine on top, we're talking 5 meter draft. So virtually any harbor will have this water depth. And then in operation, we do go, once we deploy the lower tank, of course we are deeper, but of course this will always happen in open water. So you have some details there about the design itself. And I'll also be giving you some key results on the analysis we performed again together with NREL. It was good because NREL did their own coupled analysis with FAST, and which of course they know very well, having developed it. And we did in parallel some others with other softwares. Alignment was really good, but there was a good learning and very good interaction. And just to give you, well, we didn't do the full load calculation, but we did go through the most critical load cases in terms of emergency storm, design storm, of course, operating conditions, and so on. Some results that I would like to highlight is, well, you see, we checked a lot of things in terms of forces in the turbine and the substructure, but just as a performance indicators, the movements we have in average is typically allowed to go up to 5 degrees. We're only in 3.5, so we have quite hydrostatic stiffness, and we are quite far from the limits in terms of tilt and also in terms of acceleration, which is what's giving a sense of the forces that the turbine components is receiving. We also check, which as you can imagine is relevant, very relevant for our system, is the fact that these tendons that I mentioned need to be in tension, remain in tension, and they comfortably do. So they will only lose the solidary behavior of these elements when we reach tilts of more than 15 degrees, actually 20 degrees, and of course this never happens. Yes, sir. Not only did we analyze in detail the operating conditions and configuration, but also the temporary conditions when we are afloat and we are in let's say, in barge configuration. We have very high stability, not enough stability for operation, but more than enough for this temporary condition in which both tanks are built and go one inside the other. Buoyancy is pressing them together, okay? So they're designed so that this will actually really behave just as one single body, so it's not two free moving bodies, but actually one pressed against the other. We did check through this analysis that they never lose this contact, and that the accelerations and tilts that we see are more than acceptable. Now, okay, this works very well, but how can we build it? It's good that it's compact and low draft, and this opens the opportunity to emulate some very positive experience that we've had in Spain and also in other markets in South America or in Japan, for instance, on how to build mass production serial units of concrete elements, which are really cost effective, and they are directly built on barges and floated off. This really reduces the area that we need to build these elements, also the bearing capacity of the harbors, and it's what's making it possible, as I will try to describe, to try to use existing harbor infrastructure despite the limitations that, as we know, exist in that regard in the West Coast. Okay. These are always built on a 24/7 basis using sliding formwork, and actually this, as a reference, they are built one per week as a very normal rate, despite having often 3 times as much concrete weight as we have in our floaters. So this is what we're aiming to do. Reaching a solution that can be built on existing harbor infrastructure, because we need much little area, because we build on the water, not on land. We build on floaters that tanks, and then we float them off. We have to complete some operations with installation of the transition piece, and depending on the project circumstances, also in that area, we could perform the integration of the installation of the wind turbine itself. This, well, in our case, although we have aimed for a configuration, that is, let's say, emulating caissons in the sense that it's formed by flat slabs and vertical walls that can be either with climbing forward or sliding forward, and this is quite effective and low cost. But still, there are more complexities. We do have some ballasting system. We do have some pre-stressing to make sure that the tanks will be fully watertight, and this means that we are not going as fast as caissons, but with 2 barges or a barge that is double, we can take 2 weeks, therefore deliver and a construction rate of around 1 unit per week. Okay, and this is, I will try to give you an overview of the strategy we proposed being an R&D project. That's true, but we wanted to see how it looks, what would be the typical requirements, and we looked into the West Coast, and well, I'm sure several of you may be familiar with the infrastructure that is present there, and there is planned developments in the Humboldt area, but we're looking into the Morro Bay, and it's a really big distance, plus that area is going to be, well, very much demanded, and plus it's not in place right now. Richmond and San Francisco there are some possibilities there for some areas, but not to integrate the turbine, because of course we have the Golden Gate, so we cannot tow out a system with the turbine. So what we propose, and it's something well, just as an exploratory analysis, is how this would look like if we looked into Long Beach, which of course is a very busy harbor, and it's not been so typically considered for wind, because yeah, it's of course it's based on harbor activities. But thanks, and it's very busy, and there are very few available areas. But because we need much less area, we think it could be feasible. Okay. So I'll explain a little bit the strategy we followed, and what would be an example of the layout to build in these elements. So in this case, if we build in Long Beach, we tow out with the barge configuration you just saw, and we have an intermediate operation in which we deploy the lower tank. This is done in a controlled manner with some closed chambers that we use to only with water deploy tanks. As you can imagine, the both tanks and all the suspension tendons are all fully assembled on harbor, and this we can do, like I said, close to the harbor, to the port as soon as we have enough water depth. In this case, we can do it behind Santa Catalina Island, which in addition provides some shelter. And then we have an ocean tow with the final configuration. Oh, I didn't mention, but yeah, we are using, I don't know, we are using sand ballast in the, maybe it's here, sand ballast in the lower tank. We have developed a system with pre-installed hoses and working together with Boscalis to do that, aiming for the lower cost. At the end of the day, we need weight there, and we also consider magnetite over those, but really sand is providing the weight with 1 order of magnitude lower cost, and we're trying to reduce the cost as much as possible, So that operation we do close to the harbor, and then we have our ocean tow, where we have to do the hookup, and this is, we did a very thorough analysis of the workability. That was the activity that actually governed some of the marine spread, because we have a big swell, and the average wave height is quite large, so doing the hookup was one limiting factor. So, just to have an idea, and I should stress that we didn't go into the details regarding availability and so on. We just wanted to show what would be the typical needs. So when we looked into Long Beach, we certainly don't have a very large area to do a huge Marshall import for 100 turbines. But with our approach for manufacturing, there could be some areas that, and again, we haven't done that analysis, but are not in heavy use right now, and could be considered. And we just made an exercise within Pier 46, which could look something like that. We would need 2 floating barges if we need to approach 1 unit per week construction rates. And this pier is actually not very heavily used, and we don't have enough pier length, but with seabed preparation, our floaters, which is something optional, but it can be an advantage, can be, after the float off, be positioned on the seabed, and this is a big advantage for integrating the turbine, because therefore you're going fixed to fixed, which of course is simpler. We do have an intermediate position to complete some works, but this gives an idea of the area that would be required would not be very much. Of course, as you can imagine, here we're providing area just for 6 to 8 storage of wind turbines. This is not enough, meaning that turbines would need to be fitted from elsewhere, maybe some other area in the harbor or always. But it is enough so that during the installation season, we have enough turbines to integrate them and tow them to the site. One thing we do need with this constructive strategy is some wet storage. Okay, so we are building on barges. We are floating off units, and but we are doing that, even though we can do it quite fast, one per week, we want to install them even faster during the spring-summer season, meaning that we need to, let's say, store our winter production, which is a typical way to go when we are building concrete caissons. But you do need harbors that have, let's say, some available shelter area. Again, Long Beach in that regard is very positive because there are breakwaters which generate a very, very large area where some water storage of less than 10 units could be considered. As said, to assess what would be needed, we did go through the available walls. There's quite a lot of information there to assess the workability, the number of installation windows we would need. And with that, we could size the marine spread, which in this case was governed by the hookup operation. So, but the good thing about the solution or many floaters is that we are basically using tacks, so we don't have a very heavy lift vessels or means that are very, very scarce. And with 3 installation teams in this case, we determined that a 50-unit wind farm could be installed in only one 9-month season. But yes, the hookup operation was limiting factor, and that's what determined that for this we would need 3 different installation teams to make sure that we can use all the weather windows available. Okay, so with that, I would just like to end letting you know about well, what are our next steps with this project nearly being completed, and to push the technology. One of course key aspect. Even though we have done a lot of engineering, testing, simulations, and so on, at the end of the day, we know you do need to have an operating unit in the water to demonstrate that everything works. And we will be having that in 2025. We recently got the very good news that the European Commission will be supporting our project. As STECO, we are leading a quite important international consortium with some reference companies, including, for instance, Boskalis in marine operation. Breeden Becker, who is a leading company in terms of suspension tendons. I didn't mention, but we are using the suspension tendons synthetic fibers, Dyneema, and we are working in quite detail with them, also contractors, and we are working with the smaller turbine manufacturer, 2B Energy. They're using a 2-bladed turbine. And of course, the system can work with 2 blades or 3 blades, but it's good because we have a good interaction, which is not so easy with the large turbine manufacturers. And this will be installed with a 6 megawatt unit in an around 100-meter water depth, with a budget a little bit more than 25 million euro, which is already showing that the system can be competitive because we are doing a ratio of investment per megawatt, which is for a pilot close to what is now being used for commercial projects. Also, and with this, we are working. Monica mentioned, and we are very happy when DOE suggested that we could form a team to go to the flowing price and keep working on these ideas, which I think are worked quite in detail. But at the end of the day, of course, we were in contact with some local suppliers, but we to make it real, we need to work more. So we have made, I would say, a very strong team, including a major developer, which I cannot disclose. As you can imagine, right now there's an auction going up. So really, but you can see some of the members of the team. We are carrying the engineering, and we'll have IEA, which is part of the Mastec group. It's a very large infrastructure and construction group here in the US. All collaborating with Rubber, which is a smaller Spanish contractor. They will be building our pilot, but they bring the expertise in these caisson construction techniques that I mentioned, which we think can bring potential. We have on board Sarens, which probably many of you know. It's one of the leading companies in terms of heavy lift, and there's a lot of heavy lift operations here with the ringer cranes that will be needed to install the turbines, the SPMTs to move these pieces. And also we are working with them on solutions for the construction barges, even using modular elements, and there are some good ideas coming up there. And we also have on board SSA Marine, which you probably know. There's a leading company in terms of harbor and marine operations and logistics. They know very well availability and operations in harbors. So hopefully, and we'll be presenting our candidature, and we hope we can keep working together and making this a closer reality. So with that, thanks a lot for your attention, and of course, if you have any questions, I'll be happy to take. Thanks.
Okay, so we've gotten several questions through the Slido. Zach, you were the most on time in your presentation, so you get the most questions to balance that out. So we'll start with Zach, but maybe John will chime in on this too. What geotechnical data do you need to become available to support anchor technology development? So it might come from developers or from BOEM, or what data would help you with your technology development?
Yeah, so the main thing for us is we can use cone penetration data. We can also use boring data, but it's getting offshore and getting actual offshore geotech investigation completed. Most theoretical studies aren't enough, given that you never know where the underlying layers are and they change.
And would anybody else want to chime in, or? And then, so this is for Triton. How do the helical piles have enough capacity to pull the bucket down?
So we use a combination of installation methods to get the bucket in. It's a combination of helical piles and other functions of our tool that get that install the bucket in the ground. We have a sufficient number of helical piles that each of them as a group has the full capacity to pull the bucket in.
All right, and then a question on, again, on the helical piles, are they solid or are they hollow pipes? And maybe you can just comment on like the size.
Yeah, so they're standard off-the-shelf helical piles, so they make them in two different fashions. The most common fashion is just a round pipe, so the hollowed pipe. Smallest size is around 3 inches in diameter. Largest size is probably about 8 inches in diameter for the shaft. The plates in the bottom can be anywhere from about 8 inches in diameter upwards of 24 inches in diameter, with 1 to 4 helical plates per pile. So all of our stuff will most likely be round shaft. They also do make square shafts, but those are they have some pros and cons depending on your soil types and installation methods. But the rounds seem to be the most commonly available and the cheapest.
And then another Triton question on your test at the University of Rhode Island Peckham Farm. Just how did you pick that location? Did you consider a location closer to the water, or and then maybe you can also comment if you have any future intentions of doing other demonstrations.
Yep. Yeah. So we picked this site at University of Rhode Island just because one, we've been working with them for about 5 to 7 years now, helping do geotech work. They have a research farm. The farm has a good classification of sand, and we started in sand soils, and then we're going to eventually go to clay soils with some further testing down probably in Texas. Ultimately, they just had the right site close to our location in Massachusetts, so it's not a far drive, and we could do iteration testing. As far as in the water testing, we obviously wanted to start on land, and we'll be performing an in-water test during the last stage of the ABS qualification. So when the next funding comes in, hopefully next summer or a little bit after then.
All right, and then now for Deep Reach, for the bespoke installation tower that you described, did you do a cost estimate of that, and was that included in the LCOE analysis you talked about?
No, the cost of the tower was not. We assumed it was part of the balance of system. We included a upgrade cost to upgrade it to handle the mating and the crane, but we assumed that the tower itself was included in the balance of system. So we'd piggyback on the substation.
Okay, so starting with the assumption that it was a substation tower.
Starting with the
there.
assumption there's a substation there, but we are working now on a bespoke design and a cost estimate for that, and our initial assessment is that if you amortize the cost of that over the entire wind farm, it's not going to be a showstopper in any regards.
And then there's a question, so using that tower, how is the turbine installed?
The turbine is, well, the crane installs in the cell, and then the blades are installed in a conventional way. I'm not sure I understand the question.
So would it be installed with a wind turbine installation vessel at the site?
No,
or is it installed using
the tower itself is a wind installation vessel, because you have a crane. The remote crane has the capability to raise in the cells and the blades and install them. So the tower itself is serving as a wind installation vessel.
And then did you do any cost comparison to an actual wind installation vessel? Or
No.
Okay. And then, for Esteco, there's a question, I think for the Plocan demonstration you showed, who's supplying the two-blade turbine and how big is it? What's the rating?
Yeah, it's a 6 megawatt unit, and the company supplying it is called 2B Energy. It's a small Dutch company. They have made a few pilots, but they have quite nice technology. And like I said, for a demonstrator, it's a smaller company, and we have a good interaction with them in terms of the analysis, the couple, the definition of the control, and it's going well for now. But again, the system is conceived for commercial and typical upwind three-bladed turbines. But yeah, for the pilot, it made sense to collaborate with them. Yes.
And then a question on for the wheel technology. How do you have to manage putting in the ballast? Do you have to manage it in a certain way to avoid differential tension in the lines?
Yeah. Well, when we deploy the lower tank, this is done with only water, and we have zero buoyancy. We have some chambers to do that, and the first stage we only have the weight of the concrete. Then we have two potential systems to actually deploy the ballast, and that's based on either dredges or fall pipe vessels with our hoses, or a system we like better of pre-installed hoses, so that with floating hoses typically used for dredging applications, we can pump the water into the sand into position. We're working in a lot of detail with Boskalis in that operation. They're in charge of that in our pilot, and yes, I didn't have time to give you all the details because it's a short time, but indeed it's a novel and a very important operation for our system. So we're working on that in quite a big detail. Yes.
And another one on the wheel. So during the transport phase, do you have to use any damping or estimate the damping to make sure that the two tanks don't hit each other while moving? Yeah.
Well, and they're really not free. So what we use, and that's a difference from the TetraSpar solution you see, is that we pre-stress both tanks together, but not with any pre-stressing elements or cables, but just with buoyancy. So the upper tank it's weighting, it's putting its weight on the upper tank, which is pushing up. And we can regulate this just by putting water in the outer tank, so generate more weight that goes against the other. So buoyancy forces are keeping both tanks together. So they are actually behaving just as one, and they are pre-stressed against each other. Truly, there is a moment in which we need to separate them, but this is short, and then we have a fendering guide system during this short amount of time when we ballast the lower tank, and they are separated. But during the towing operation, when we are towing out of the harbor, there are not, let's say, two elements moving together. They're actually pre-stressed against each other, so they really behave as one. And what we did in our simulations, and we will also be doing in the tank testing, is making sure that pre-stressing force we generate is enough, so that they will never separate, and we don't have any, let's say, movement or contacts or impacts. Yeah.
And then one more, you mentioned the TetraSpar. How does that compare with the wheel design as far as material and cost?
Well, it's based on the same concept. As said, we were happy to give Tetraspar a license of the system because we think it's also helping our technology, and we are in a collaborative approach with them. It's quite different. They are all based on steel. So yeah, it's a lighter solution, as you can imagine, in terms of overall weight, but then steel is more expensive. In our case, we think especially for the lower tank, we need weight, and it's cheaper to generate that weight with concrete and sand. But other than that, it's a similar concept. There is also a difference in what I just mentioned on the strategy and how to go along these temporary stages. So in our case, both tanks are pressing against each other when we're towing out. In Tetraspar used the lower tank was also hanging when they were towing out with some special winch system. There are different approaches. So in operating conditions they are similar. In some of the temporary stages we're going with different approaches. But and the overall, we are collaborating. I don't have all the details on their materials and cost, but we are expecting that concrete can be more cost efficient, but at the end of the day, it's a big market, so it's I'm sure there's opportunity for different type of solutions. Yes.
All right, and then back to Triton. So you showed us the anchor that had 9 screw piles in it. So what would happen if one of the helical piles were to strip or otherwise fail during installation?
Yeah, so we have redundancies built into the system where we have additional helical piles for safety factor reasons too. So basically, we have extra helical piles. So if we lose a couple during installation, or if we can't install them to the full depth, per se, if the expected depth is 40 feet, we only get them to 35 feet. We have additional anchors in to achieve the ultimate capacity. We also measure installation forces as we install it, and that validates our ultimate capacity once installed.
And then does the anchor concept work better in sand or soft clay?
If you asked me a year ago, I would have said sand. We're finding some interesting stuff out in our clay analysis with Texas A&M that is showing a lot of promise. So actually right now I'm not too sure. I would say in sands we're sure it's cheaper than pile solutions. In clays we have not run detailed cost assessments yet, but I would say it's getting to be pretty cost competitive, if not better, in clay now.
And then for deep reach, do you consider a multiple cell spar to have a fully autonomous fabrication like the single cell spar?
The units, the cells themselves, yes, we would have to do assembly of the cells either on shore or on a barge.
And okay, I guess for everybody, what turbine size are you expecting developers to select for California projects?
We've been receiving 15 megawatt load cases.
I don't have an answer to
All right,
that.
and you were tending to use the 15 megawatt design reference turbine.
I shouldn't give details, but I think several of them are considering even larger turbines. Yes, I would say yes.
Okay, and then for Esteco, are you considering concrete 3D printing?
Well, we're following it. It looks interesting. To be honest, we are not experts, and we like to keep things that we know very well about, and we're very familiar with pre-stressing and designing conventional concrete. And also we see that in the market, we're already having innovation with the cables. So if we keep it to one innovation, it's easier to go into the market. But nevertheless, it is promising. But for pilot and so on, we're still not considering that new technologies. Also considering the size of the elements we have, we claim to be smaller than the competition, but still 50 meters. It's a large structure. Yes.
Sure. And then for the Triton anchor, are the helical piles, are they considered removable and potentially reusable at the end of project life?
So we have two ways of decommissioning. One way is that our installation tool is able to remate to the anchor and unscrews the anchor and pulls the system out. Obviously, after a 30-year lifespan, that might not be possible. But by using smaller piles in a group configuration, one single pile of the helical pile is easily removable. So we can basically pluck out the individual piles and then ultimately removing the system. So now if you could reuse them or not, I mean, I guess it depends on how much degradation there is over the 30 years, but there's definitely a recyclable metal potential, there.
All right, and I think we've gotten through just about all the Slido questions. So it's kind of as we wrap up, could you comment on who you're marketing to, who would like make the decision to use your solution, and then also kind of like what vendors are you engaging with? What kind of workforce skills would be employed for your technology?
He's the flow-in guy, living.
Well, in offshore wind, as opposed to onshore, we are also quite active. And when we're talking about substructures, the natural client is a developer. In onshore, it's typically the turbine manufacturer. But in this case, offshore is typically within the scope of the developer. We'll use different packages. So that's the natural end user of our solutions. Regarding the other question about the workforce that we will be engaging, well, one thing that we're trying to pursue is the fact that there may be some bottlenecks regarding shipyard capacity. There may be some new ideas, like John mentioned, which look really interesting. But concrete labor and concrete works, it's really available anywhere, and it's not very skilled labor, and it's very high local content, both in terms of raw materials and like I said, workforce. So I think that's a good potential to generate in economic benefits where the units will be actually built and used instead of bringing them from elsewhere. Yes.
In our case, I think our business our business model is still in the development stage. Our conversations have all been with developers up to now, particularly Equinor, because we know the Equinor people and they've been kind of encouraging. But this is a relatively new development. We haven't been working on it for years, although spars, we know they work. So that's the background. We're waiting to get the results of the speed study we're doing on the manufacturing. We would like to have confidence that we could stand behind that concept before going forward. So we haven't really stepped out and engaged with other than the people that would do the manufacturing with us. We haven't stepped out very far beyond ourselves. Although we have people on our team that were heavily involved in the fabrication of the East Coast platforms down in Louisiana, and we know the Gulf Coast fabrication yards. We're based in Houston. All the Deep Reach and Transit are based in Houston, and we have on our board of directors, we have people that ran the shipyard and Gulf Island fabricating yards, and so we have a lot of fabricators hovering around that we're talking to.
Okay, but more still needs to be developed in future.
The actual business model, we haven't really settled on it.
Sure.
Yeah, as far as our customer interaction goes and our decision maker, it's basically two options. So option one is directly from the developers, as they're going to be the owners of the geotech data. But the other model that we've actually seen come up even more is the platform designers will have basically preferred anchor suppliers for their solutions, and they would probably recommend an anchor choice to the developer, as the developer is most likely going to select the platform before they select the anchor. So two of our decision makers have basically either been platform designers or developers. As far as workforce development and kind of people that we expect to hire, our business model is pretty well defined right now, and we have a pretty good 5-year plan. We expect to hire kind of global project managers at certain sites as we achieve commercial contracts, and then we'll be hiring local fabricators to ports to do metal manufacturing.
Okay, and then do you want to announce what's next?
Yeah,
Okay.
yeah, thank you.
And we'll give a hand to the panel.
Great, so thank you all for coming. Thank you, Monica, for moderating in the panel. Just now, we're coming up to a 30-minute break. There's coffee and refreshments back in the main room down there. And then the next sessions will start again at 3:15. There's the next floating wind deep dive in here starting at 3:15. So see you back here then.